Welcome to you all. Now we said that we are interested only in real values, right? Only in real values. Although we are bringing in the complex phasor notation, we are interested in real values. That means as this slider rotates, or as this crank rotates, okay, and this mass does oscillatory movement, this mass is doing oscillatory movement back and forth. So either a cosine omega t type movement or a sine omega t type movement. Okay. So then how do we get it back? We get it back by saying that a cos omega t, okay, which could be the movement of this mass. This mass could be moving like a cos omega t, okay. This is equal to the real part, okay, of a e to the power j omega t. Okay. So this crank is rotating at e to the power j omega t. It is rotating as e to the power j omega t, and therefore there is some amplification due to this, okay, slider. And so let's say that slider has an amplification and becomes a e to the power j omega t. Okay, and out of that I am trying to pull a real value movement for my mass. Okay, so it's the real part of a e to the power j omega t, or the imaginary part, whichever I want. Okay, and this angle that is covered, omega t, is the phase angle. Okay, so we said that we will consider the starting to be vertical at pi by 2. Okay, so the phase at any instant for this first mass, okay, is going to be measured from here. So it's going to be omega t plus pi by 2. Okay. Now how does it work out? So in t seconds, the phase covered by the phasor is twice pi. Okay, and so in 1 second the phase covered is twice pi by t, which is omega. Okay, so in small t seconds the phase covered is omega times t. This is actually a non-dimensional number, that's why it's an angle. Okay, non-dimensional number. Okay, so that is what is covered by the phasor, and to that you add the reference value, your starting value. So that happens to be the phase of the first mass point, and beyond that is our spring. Okay, beyond that is our spring. Now let's see over here. The information as it travels along the spring, it takes time, right? We said c is the speed, so it takes time to travel. Okay, so if I assign a phasor to the starting point, let's say that phasor we will align with the original phasor here. We will, okay, so it moves, its own descriptor moves like this, and we assume there is an amplification a, so let this phasor be a times e to the power j omega t. Okay, this a is unimportant, but let's just keep it, because if we say this is 1, and there might be some amplification of a over here, so well, let's keep it. Okay, now as the pulse moves along the spring, if I look at a certain location x1, okay, it is delayed, so it will see the information at a later time. So the phasor should be representable here as e to the power j omega t minus something, minus some quantity. Okay, but omega t being the phase or being the angle, this should also have the same unit, a non-dimensional angular unit. Okay, so now what should that be? What should that be? Now we say that wavelength happens to be the distance between 2 points. Let's say these are 2 points. Okay, wavelength is the distance between 2 points undergoing similar motion or same motion. That means the phase is twice pi, right? Because the phasor went around once and these 2 points were generated. So the phase difference between them is twice pi. So over lambda distance, okay, the phase covered is twice pi. So over unit distance, the phase covered is twice pi by lambda. Okay, so over a distance x1, the phase covered is twice pi by lambda into x1. Okay, so at x1 location, the phasor will be denoted by e to the power j omega t minus twice pi by lambda x1. That is the amount of phase delay. Okay, this is the phase delay over unit distance. This is the phase delay over x1. Okay, so that's the amount of phase delay. So that is what the location at x1 will be seeing. Another location x2, let's say, okay, another location x2 will be seeing e to the power j omega t minus twice pi by lambda into x2. Okay, and similarly, if there was a point lambda away from x1, okay, e to the power j omega t minus twice pi by lambda into lambda distance. So it will be seeing e to the power j, sorry, let's call it x1 plus lambda. Let's do this here. So let's say twice pi by lambda, and it is lambda upon more than x1. Okay, so this is going to be equal to e to the power j omega t, okay, minus twice pi by lambda x1 minus twice pi. Okay, so twice pi gives me just 1. So a point lambda away from x1 behaves like x1. So that's the answer I get. Okay, that's the answer I get. So now if we look at my spring, so this mass, first mass is moving like e to the power j omega t at a distance x1. I have a phasor that moves like omega t minus twice pi by lambda x1. At a distance x2, I have e to the power j omega t minus twice pi by lambda x2 and so forth. and if my x is a continuous variable, not discrete points, I will say the description along the spring for a continuous variable x is twice pi by lambda x. Okay, x is now continuous along the spring. It's a continuous variable along the spring, not discrete points. This entity twice pi by lambda, which is actually phase change, per unit distance, is given the symbol k and the name wave number. Okay. Wave number is a very important entity in acoustics and sound structure interaction. Okay. This symbol is dedicatedly used for wave number. Okay. So that means what? The wave description has become e to the power j omega t minus kx. Okay, e to the power j omega t minus kx. Okay. So now, just to drive home the point a little bit more, I will take stations. This station is right here, the 1. Okay, I mean sorry, 1, the mass, the origin. Okay, I take another station a little to the right, one more little to the right, one more little to the right, and maybe the last one. And this is my spatial direction. This is my spatial direction. Okay, and this below vertical will be my temporal direction. Okay, this way is my temporal direction, increasing time. Okay, so let's say here I begin as before as a vertical. My phasor is vertical. Okay, phasor is vertical. Now this point a little bit later is delayed. Okay, so that phasor is, let's say, some 22.5 degrees behind. Okay, another point to the right is, let's say, 45 degrees behind. Okay, why is that? Because it's e to the power j omega t and delayed by k times, let's say, x1 x2, k times x2. Okay, similarly this one is, say, delayed by 67.5 degrees, and this is delayed by 90 degrees. Okay, now here what do we have? This is advancement in time. So the phasor, let's say, moves forward 22.5 degrees, and here it is 22.5 degrees behind, so this is going to be vertical. Here it's further 22.5 degrees behind, it's going to be here. Here it's going to be 45 degrees behind. Okay, and here it's going to be 67.5 degrees behind, and so on. Here this will be 45 degrees ahead. Here it will be 45 degrees ahead. Here it will be 22.5 degrees ahead. Here it will be vertical. Here it will be 22.5 degrees behind. Here it will be 45 degrees behind. Okay, so here this will be 67. My angles are a bit off, but here this is 67.5 degrees ahead. Okay, here it is 45 degrees. Here it is 22.5 degrees. Here it is vertical. Okay, here it is 22.5 degrees behind, and so forth. Okay, and all points in between. X is a continuous variable, time in a continuous variable. So every point in a wave transmitting system or a wave bearing system has a phasor description. Phasor, I'm having some trouble here, so let's see. Has a phasor description. Okay, of this form, e to the power j omega t minus kx. Okay, at some reference x equal to 0, whatever it may be, okay, you choose, it is going to be e to the power j omega t. Okay, so you can consider that to be your reference for phase. Many times this happens to be the forcing agency. So your forcing agency is f e to the power j omega t. So the rest of the response is phased with respect to the forcing agency. Okay, and therefore the absolute phase is not important. It is with respect to any reference that you choose. Okay, here we said our phasor moves starting from vertical, so we tied that to the mass. So we said, let's say that is the phase of your mass. Okay, then everything else starts to move relative to that phase, and so you have this description, e to the power j omega t minus kx, where this was described as e to the power j omega t. If this is described by e to the power j omega t plus pi by 2, doesn't matter, this pi by 2 will get added everywhere. Okay, so that the relative difference between the two is the same. Okay, now let's see. We go now to the very first important idea in sound structure interaction. Okay, main or central idea in sound and structure interaction. Okay, in order to do this, we will need the two-dimensional acoustic wave equation. I'll write it like this: AWE, acoustic wave equation. In rectangular coordinates, it's given by del 2p del x square, okay, plus the way I'm taking my coordinate is del 2p del z square is equal to 1 over c square del 2p del t square. That means the p is a function of x, z and t, x, z and t, x, z and t. Okay, so we'll need this equation, 2D acoustic wave equation. We will also need the plate equation, okay, governing the vibrations of a plate, a rectangular plate. Okay, what is that given by? That's given by a constant in front, okay, del 4 W del x4 plus twice, let's say, twice del 4 W del x square del y square plus del 4 W del y4 plus mass per unit area del 2 W del t square, that is equal to 0. This is the equation of motion for a vibrating plate, okay, vibrating rectangular plate, okay. So we will need these two equations. Now, so what is the system we are looking at? We are looking at a system. Let me draw it small first. So we have a plate, rectangular plate, so this is my x, that's my y, that's my z. So we have a rectangular plate that is vibrating, okay, and it goes off to infinity in this direction, it goes off to infinity in that direction, okay. So above the plate we have a region, we call it the acoustic half space, acoustic half space, okay. So as if the region has been divided into two halves, the world has been divided into two halves, one above the plate, one below the plate, okay. Now further, as this plate vibrates, we will assume that the dependence on y is not there. So the displacement W earlier is not a function of y, not a function of y. So all y derivatives will go to 0. All orders of y derivatives go to 0. So the plate equation kind of looks like the beam equation, okay. So I have d del 4 W, this time only function of x and t, del x4 plus m dash del 2 W by del t square, that is equal to 0. So this actually looks like a beam equation. However, this is E h cube by 12 into 1 minus nu square, okay, and therefore, so we will call this a 1D plate, one dimensional plate, one dimensional plate, okay. And therefore what happens, this picture now, this picture gets modified. So there is a one dimensional plate, okay, which goes off to infinity in both directions. So it goes off to infinity in both directions, and there is an acoustic half space, there is an acoustic half space. Okay. Now on this one dimensional plate there is a wave moving, it has been initiated, there is a wave moving, and what does it, what is the description? W of x comma t is a e to the power of j omega t minus k plate x, okay. So by now you should be used to this notation, right. This is the description of a wave moving on a wave bearing system, right. So omega is in my control. So at some distance very far away there is a disturbance given, okay, very far away there is a disturbance, maybe a point force is applied, and so that starts off a wave, and that wave, by the time it arrives at where we are, it looks like this. Okay, and then Kp happens to be the wave number in the plate. Okay, I should have mentioned earlier that this wave number in the structure Kp depends on frequency, and it depends on the stiffness and the inertia properties. Okay, earlier we were talking about the spring. Same thing, when the phasor is rotating, and it's connected to the mass is connected to the spring. What is the wave number in the spring? It is dependent on the frequency omega and the stiffness and the inertia properties of the spring. So these three independent variables decide what the wave number is going to be, and therefore what the wavelength is going to be, because why wavelength is what? Wavelength is twice pi by k. Okay, so wavelength and the inverse wavelength wave number are decided by these three properties. Okay, so Kp in the 1D plate got decided by omega and its properties. So this is my descriptor of the wave in the 1D plate. Okay. Now my question is, this wave excites the sound field, excites the sound field above the plate. Okay, so what is that sound field? Okay, this displacement on the 1D plate results in what sound field in the acoustic half space? So let's see that. Okay, so we gave the acoustic wave equation earlier for a 2D rectangular region. Okay, it was given by del 2p del x square plus del 2p del z square is equal to 1 over c square del 2p del t square. Okay, for you should know now that this has a solution, wave solution, given by some constant in front, e to the power of j omega t minus kx x minus kz z. Okay, there is an x component of the wave number, there is a z component of the wave number. Okay, so there is this 1D plate, the acoustic half space. So in the acoustics half space, there is a wave number in the x direction, there is a wave number in the z direction, and therefore a resultant wave number in some direction, so, which is the acoustic wave number. Okay. Now the wave number we said was twice pi by lambda, right? Twice pi by lambda is k, the wave number, right? Okay, and we also said that c is equal to f lambda. Okay, or lambda is equal to c over f. Okay, so I have twice pi by c, f is k, wave number. Twice pi f is omega. So therefore omega by c is k. This is very important. The moment you know the speed of the sound wave in the medium, the moment you know the frequency, wave number in the medium can be found. Okay. So we are actually exciting the beam at omega frequency, right? Okay. And so the sound field being a linear system, it will respond at omega. So sound field will respond at omega. And we know, let's say the medium is air, we know the speed of sound in air. So omega by c is known to us, is known. So this k is known to us. The moment frequency is given, k is known to us, k in air. Let's say this medium is air for now. Okay. So now if I substitute this into this, substitute this supposed solution into my original partial differential equation, you can see I have two space derivatives, I have two z derivatives, I have double time derivatives. So that will actually give me, without full derivation I will tell you, that kx square plus kz square is equal to k square. Okay, you can try it out, you will get this. Now I said this k is known to me, why? Because omega is known to me and the speed of sound in air is known to me. Okay, but kx and kz are not known to me, they are not known to me. Okay, so they have to be fixed. How do we fix that? Kx is the x direction wave number, that means the wave number in the in the x direction, and kz is the wave number, the variations in the z direction, describes the variation in z direction. Okay. So let me close the lecture here for today. We will continue with this the next class. Thank you.